All right, this time include the damping. So I usually put constant gamma here rather than beta, but I'm using beta because I often use gamma in this way of writing things when I'm thinking about a spring mass system with damping in the spring. So kind of like this, where I'm using m gamma k. Now I've divided everything by m, and so this is gamma over m really. I'm just going to call that beta. Okay, so just to avoid some possible confusion. So here's our damping term. And same question. Oh, actually wait, sorry. This is omega, which may or may not equal omega naught. It's just omega. And my question is the same. So how does the response of the system, so the solution of the system, react to various choices of omega, the driving frequency? So you're going to do, to analyze this, you're going to do the same thing basically, where you look at, you'll get a general, get your fundamental solutions, your general solution to the homogeneous version of this, where you set this equal to 0, and then you somehow, probably using the method of undetermined coefficients, get a solution to the non-homogeneous, the full this thing. So by some means, even guessing, method of undetermined coefficients, you get a solution. And then you add them. So one thing that's different and that actually makes it easier to analyze this situation is that what you get here will decay. So let's actually get into it a little bit here. Mainly I want you to look at this on your homework, but I do also want to get into it a little bit to make some comments. So what will we get here? So we'll guess e to the lambda t, right? I think we've done basically this very similar thing to this before. Guess e to the lambda t. Then we get lambda squared. We get this characteristic polynomial, right? And then you get you use the quadratic formula and you get these two roots. Well, they could be two roots, or they might be one root actually. And depending on how big beta is, if the damping is very large, beta is very large, then what's under the square root here will be positive, and you're looking at two real roots. But as we've discussed before, I think for this kind of damped harmonic oscillator situation, they are negative. So these end up being negative real numbers when what's under the square root is a real number. These end up being negative real numbers. So your general solution to the homogeneous is just going to have exponential decay terms, which is what you expect, right? You wouldn't expect exponential growth from a system that's dissipating energy, right? Exponential growth is like it's gaining energy for no reason over time. That'd be weird. So unsurprisingly, this is leading to exponential decay for the general solutions. That's in the overdamped case. In the underdamped case, where beta is small, the damping is small, then what's under the square root is negative, and you have complex roots. But the complex part basically is this, or the imaginary part ends up being the part that has a real number times I is this part, and then what is the real part? It ends up being this, right? Which is negative beta over 2. Beta is positive here. It's negative beta over 2. And so that real part is going to be the exponential rate on an exponential factor in front of the entire solution in the overdamped, or in the underdamped case, which will also decay. So in the overdamped case, you have two decaying exponentials for your fundamental solutions, and in the underdamped case, you have oscillation multiplied by a decaying exponential again. So no matter what, this will decay. So, no matter what, this decays. Decays no matter what. That is what damping does. So the portion of your solution that has this will end up being what we refer to as the transient part of your solution. So right at the end you'll have like C1 x1 of t plus C2 x2 of t, where the x1 x2 are what you get from step 1 here, and then from step 2 you get an x particular, right? since this will decay, this will be the transient part. So I'm not saying that always happens, that the general solution to any homogeneous differential equation will be a transient part. I'm not saying that. I'm saying here, where you're looking at a damped harmonic oscillator, this seems to end up decaying always. So this ends up being the part that is transient. It dies off very quickly, and this part dominates. So you pretty much, to understand what's going on, you can pretty much just look at this. That makes this situation a little bit easier than the undamped situation, is that you can understand what's going on long term by just looking at this part. So the steady state part of your solution ends up being basically the x particular that I'm talking about, the one you get from the method of undetermined coefficients. Okay, so that's one comment. And another comment, so I think that's enough to, I think you now have enough information to go and try that homework problem. But so I taught this course in the fall quarter of this year, and I remember this particular problem where I was having you look at this kind of situation very well because of how many people a certain aspect of it confused. Here's what ended up confusing people. When using the method of undetermined coefficients, you end up having to solve a certain linear system in the undetermined coefficients. It seemed to throw a lot of people off that the parameters here, like omega and omega naught and beta, are unknown. Actually, in your homework problem, I think there are some of those parameters are known, but not all of them. And it seemed to throw a lot of people off that there were unknown parameters. So my advice is pay attention to what it is you're solving for and what you want it to be written in terms of. So let me just get it started. So here's the guess that you're going to make for the method of undetermined coefficients. We have a sine omega t that we want to come out. So judging by this table, I should guess something sine omega t plus something cosine omega t. So that's what I would guess. It can be sine omega t plus c cosine omega t. And then there's a lot of calculating involved here, because you need to now plug this in to the left-hand side here. And then set that equal to the right-hand side here, and try to see what b and c have to do to make that true. So when you do this, so when you plug all this into the left-hand side, so you're going to plug this into the left-hand side, right, and set it equal to the right-hand side. So when you plug this into the left-hand side, you'll do a whole bunch of calculating to get something. And that something, you can rearrange the terms to get it to look like a whole bunch of complicated stuff times sine omega t, plus a whole bunch of complicated stuff times cosine omega t. And then you'll set that equal to a sine omega t. And all of this complicated stuff here is going to have some little b's living in there. Maybe in multiple places, I don't know. And it might have c's living in there too. There might be c's in there. And what you're going to do to get your equation is the same. This is basically the same thing we were doing. It's just you have more complicated stuff to deal with. These are going to be more complicated since the left-hand side here is going to involve this first derivative also. So what you're going to do is match this up with this. So one of your equations is going to be this. So that's one equation in your system of two equations. And then here, this is plus 0 cosine omega t, right? So here's your other equation. This equals 0. So there's your two equations. Whatever you got here equals a, and whatever you got here equals 0. Two equations, two unknowns, b and c. So this threw a lot of people off, because in addition to the blue b and c here that you're solving for, there are also some distractions like omega hanging around and beta, although I think I did fix beta in your homework problem. But there are some distractions floating around. Don't be scared of that. Just do algebra or linear algebra in the way you normally would and solve for b and c in terms of the other stuff. So the goal is to get to something like this. B equals C equals, and then stuff that involves, you know, maybe some A's can be in there in some way. Some omegas are allowed to be in there. These are all parts of the problem. But don't have other B's and C's in there. Then you haven't solved for B and C. Okay, so that is advice for if you get stuck with the algebra, you're not sure what algebraic steps to take. It is an involved problem in terms of the algebra. All right, so good luck with that. Here's the problem that I'm talking about, by the way. It's problem 2. Okay, and yeah, I think this one is a lot of fun. So you will end up having to do, yeah, now that I'm staring at it, I see another place where I can help answer some questions with this one. You'll end up having to, you know, you will find out what is the amplitude of the steady state part. So what does steady state part mean? That means basically what you get from using the method of undetermined coefficients, because we know that this part decays no matter what. You don't even have to bother with it. That's the nice thing about this case. So you only have to worry about this part. This part decays. So you only have to give the steady state part. This says even determine the steady state term. So you only have to provide that. Then what is the amplitude? So you just write things in phase amplitude form. Then you try to maximize that amplitude. So you see what would maximize it. That was easy to do. Thinking about what maximizes the amplitude, that was easy to do back here when my amplitude was, you know, something like A over this. I know that just if I make omega very close to omega naught, that will make the amplitude as big as possible. But you will have something much more complicated for your amplitude. So you'll have to use calculus to maximize it. And then you will figure out where resonance occurs. This is really, I think, a very cool and interesting problem. Problem 2.